Alright, so I thought I'd just try a few random problems from the book and see how we do. So for example, how about I do the following? I'm going to pause while I write this down. Alright, so this is a kind of an interesting problem. Evaluate the following derivatives. The first one is the integral from 0 to 1 of the derivative of e to the inverse tangent of x dx. You might compare that with the derivative of the integral from 0 to 1 inverse tangent of x dx. And we might compare that to the last one, the derivative with respect to x of the integral from 0 to x e to the inverse tangent of t dt. So the key here, I'll give you a hint, is that the notation is really important. Go ahead and pause, see if you can solve the three problems, and come back in a sec. Are you back? Did you solve them okay? So in this first case, we're just taking the definite integral, right, of f prime of x dx. And so that's going to be f of 1 minus f of 0. So in this case, that would be e to the inverse tangent of 1 minus e to the inverse tangent of, of 0. Okay, so that's, let's see, what angle gives the inverse, or what angle produces a tangent of 1? That would be pi fourths, right? So that would be e to the pi over 4 minus e to the 0, which is e to the pi over 4 minus 1. Good. All right. Compare that with the next one. The derivative is 0. Why is that? That's because, like we said before, this thing right here is a number. And what is the derivative of a number? It is 0. Good. And so let's take a look at the last one then. What would the derivative of the integral from 0 to x e to the inverse tangent of t be? Do you recognize that as the fundamental theorem? Because that's what that is. And so what you're looking at here is that we're taking the derivative of the inverse, or of the integral from a to x f of t dt, which is f of x. And so in this case, it would just be e to the inverse tangent of x. Very good. So that was kind of a nice problem just to be thinking about what our notation means. Okay, I'll pause it here and write up a new problem. Okay, how would we integrate the cosine of the natural log of x divided by x? I'll give you a sec. Go ahead and pause. Are you back? I think probably the most natural substitution would be u equals natural log of x. So that du is 1 over x dx. And now when we integrate, we would have the cosine of u times du. Good. And so that's just going to be the sine of u. And u is natural log of x. Right, plus c. Good. And of course, you could always double check these, right? Because if you differentiate the sine of the natural log of x, you get cosine of the natural log of x times 1 over x. Right? And so you're back to where you started. Good. How about the integral e to the square root of x dx over the square root of x? Let's see, which function would you like to make the substitution? Go ahead and pause. Are you back? I would probably make u be equal to the square root of x, and I'm thinking of that square root of x on the top, not the bottom. So then my du would be 1/2 x to the minus 1/2 dx, or 1, I'm going to go ahead and bring the 2 over. 2 du would be 1 over the square root of x dx, right? And so therefore, when I make my substitution, I'm thinking of pulling out this 1 over square root of x dx, right? That's for my substitution. And so the integral would become the integral of e to the u du. And so we just get e to the u plus c, which is e to the square root of x plus c. Very good. All right, are you getting the hang of these? Let's see, should we try another one? Maybe another trig function. Here, I'll pause and look for a good one. You know, I think I should do some really common substitutions that you see all the time. And so, where you see substitutions being made just kind of as a routine would be something like the integral of e to the 3t dt. Right, because then you would just let u be equal to 3t, and your du would be 3 dt, and so then you would have your 1/3 there. Okay, and then we would just take e to the u times 1/3, right, plus c, which would be 1/3 e to the 3t plus c. Okay, so that would be a real common integral to have to work out using a substitution. Another one might be, you know, cosine of 2t. Right, then your u would be 2t, and your du would be t dt. Oops, with a 2. What am I writing? That's 2 dt. And then you can take 1/2 du is your dt. Okay, and then your integral will become the integral of cosine of u du. So then you with a 1/2. So then you can write that as 1/2 sine of u, which is 2t plus c. Good. How about something like the integral of the 4th root. Jeez, getting tricky here. The 4th root of u minus 1, plus 1 squared du from 0 to 1. Well, did you pause? Or did you think about that? Well, because this is just a square, I think we would probably just square everything out. Right, so what's u to the 1/4 times u to the 1/4? It would be u to the 1/4 plus 1/4, which is u to the 1/2, plus 2u to the 1/4 plus 1. And then we would just integrate that from 0 to 1. Okay, so that was a trick question because that's not really a substitution, is it? But it was in the homework section, so I'm not sure what was going on there. Okay. Maybe some of these don't require us to do it. How about, okay, we'll do one more substitution, I think. How about the integral of x plus 2 divided by the square root of x squared plus 4x dx. All right, did you guess that u is equal to x squared plus 4x? So that du would be 2x plus 4 dx. Let's see, I see an x plus 2, but not a 2x plus 4. So I could rewrite that as 2 times x plus 2, right, dx. And then I could make that 1/2 du. Just to make sure that I have the same thing here that I have here, right? And so therefore now I can go ahead and make my substitution. 1/2 du over the square root of u. So I would rewrite that. Minus 1/2. I did that error before, didn't I? So let's see, that would be u to the 1/2 power times 2, but then I have times, well, oh, hey, that's easy. So that's the square root of x squared plus 4x plus c. There you go. Okay, so my time is pretty much up for this time. I may try to put another video up just as a general review. But you might take a look at the Chapter 5 review. I'll put up some review questions. And really, between now and the exam, final exam, I would recommend just going through all the different individual review sets and just working through a few problems. I would try to take maybe an hour a day just to set that aside and just work through problems and see what you're rusty on, and then make a note of the things that you're rusty on, and then go back and look at those topics. All right, I hope you've enjoyed Calculus 1. It can be a challenge, but once you're through the calculus sequence, mathematics does continue to be a very interesting thing to study. People tend to think that math kind of stops at calculus, but there's lots of beautiful and wonderful things beyond. So, all right, good luck on your final, and I'll talk to you later.